We have done a lot of the content in chapter 10 before. So we're really going to bring these ideas together. We saw some of the calculations that we need, like the molar mass. We began working with that in chapter 3. We saw it again in chapter 6. Now we're doing it again in chapter 10. The worksheets begin with sort of a diagram to remind us of how the mole units work. Now we're looking at chapter 10. It's worksheet number 11. We started the quarter off looking at chemical equations, and in this example, in this picture here, we see that the hydrogen molecules react with the nitrogen molecule. The atoms rearrange and form new substances. So the hydrogen is gone in this case, and we have now formed the two ammonia molecules. We can think about this in terms of how many molecules react, or we can think of those as ratios, that number ratio. So if I had 1,000 molecules each, right, this would be 2,000 hydrogens reacting with 1,000 oxygens to form 2,000 water molecules. Or I could multiply by any number, right? This would be 2n, n, and 2n. So what we do in chemistry is we use Avogadro's number as our counting number, and then we can just say how many moles. That gives us a word for it. 2 moles of hydrogen react with 1 mole of oxygen to form 2 moles of water. So this is exactly what we determined when we did our stoichiometry lab. What I'd like to do in this section is use this equation. This is a combustion. It's burning in oxygen. How do you recognize combustion? So I'm going to go ahead and write that. Is burning in oxygen. So it's usually reacting with just oxygen, and in the answer mentioned that it's usually a lot of carbons and hydrogens. This is a hydrocarbon, ethylene. It's a common fuel type, and sometimes there's an oxygen in there now. We put some ethanol into our gasoline, so you'll see that on the pump if you're buying gas. And the thing about combustion is that it always produces CO2 and water. Sometimes it might produce other stuff. It might not burn completely. If you have a fuel type that has 12 or 15 carbons, it's a really big molecule, you might have incomplete combustion where you would get these partial molecules left over, and those give you that black, greasy soot. So we can't balance those equations when it's an incomplete combustion. So we will only balance equations that go completely to CO2 and water in a complete combustion. In order for it to be a complete combustion, you have to have lots of extra oxygen. And so that's why we blow on the fire to make it flame up, to get extra oxygen in there. Okay, so that was a little side note. We'll get back to these relationships. Now, what I'm really going to look at here are the coefficients in front. That gives me the number relationship between the particles in the equation, and I can use moles to express that. So in this case, for every 1 mole of C2H4, I require 3 moles of oxygen. So it's a lot of oxygen is required. That's why it's possible to be oxygen deficient and have that smoldering, sooty smoke. Okay, that would produce, the complete combustion would produce 2 carbon dioxide and 2 water molecules. So from this chemical equation, we can get any relationship between any 2 of the molecules involved in the equation. So if I need to know how much carbon dioxide is produced for every fuel molecule, for every ethylene, I can just use those coefficients. I know that 1 C2H4 is going to give me 2 CO2. Now I know that at the same time that I produce those 2 CO2, right, I'm just using that coefficient, I'm going to need to use up 3 oxygen molecules, right? So we can always write a relationship, the mole-mole relationship coming from the chemical equation. So earlier in the quarter, we started doing this using the relationship within the molecule, the atoms to the molecule. The same thing works for the coefficients on the equation. So for every 1 C2H4, we're going to consume 3 oxygen. For every 1 C2H4, we would produce 2 water molecules. So you can find relationships between any two things. And that's why we construct that mole-mole relationship. So now we're going to use that in our stoichiometry. Here's another combustion. This is a propane molecule. So this would be like your camp stove runs on propane. 1 propane molecule requires 5 oxygen. And it burns really clean. It's a nice small fuel, right? So you usually get no soot. So we're going to use our unit factors, those mole-mole relationships, to figure out how many moles of oxygen. So I'm going to write down that question. How many moles of O2 are needed, there's my equal sign, to completely react, because it has to be complete, with 2.50 moles of C3H8. Using dimensional analysis, I need to cancel out moles of C3H8 because they don't appear over here. And I'm going to use that same unit, the units match, and I'm changing the label. So this is moles on top, moles on the bottom. And now I want to see, I'm looking for oxygen, so I'll fill in oxygen there. Now in the next step, I'm going to use those coefficients. So I'm going to look for what's in front of oxygen and put that here. I need 5 moles of oxygen for every 1 mole of propane. Now you put that in your calculator and you're going to get 7.5, but you have 3 significant figures. So we will keep that. 7.50. Is that right? I'm going to put it in the calculator because I feel like it's always the arithmetic that's tricky. That's 12.5 moles of O2. So we'll do the same thing for these other ones. Go ahead and get some practice here. Writing the question. How many moles of CO2 can form when 3.50 moles of oxygen are used? So at that point, I've really just rewritten the question. Use that mole-mole relationship to change the label. All right, then we're looking for CO2, so I'm going to put that on the top. And now I'm going to go get the numbers that make that relationship true. So we get 3 carbon dioxide for every 5 oxygen. And here is where our calculator says 2.1, but we have to add that 0 to show the 3 significant figures. Cancel out what we're getting rid of. Use a mole-mole relationship to change the label to what we're looking for, and then find the numbers that make that relationship true. All right, we have one more. Okay. Next up, we're going to put it together. So that was that middle step right in here. Changing the label using a mole-mole relationship from moles of the thing that you're given to moles of the thing that you're looking for. Now on each end of there, we can use the molar mass. So that allows us to do mass to mass calculations. And it always goes mass to moles, moles to moles, moles to mass. We can never go directly from mass to mass. So let's do this same process. I'll leave an example problem up there. We need to calculate the mass, so how many grams of CO needed to react with 50 grams of iron 3 oxide. Okay, so go ahead and get started on that calculation. And we're going to step through it using dimensional analysis. I know that I need to cancel out grams of iron 3 oxide. And the thing that I know that is true for iron 3 oxide is how much the molar mass is. So 1 mole of Fe2O3, and then we have to do that side calculation, right? We have to figure out that mass. Okay, now we're in moles. I don't see moles, I'm looking for grams of CO, so now I can change the label. So I'm going to cancel out moles of Fe2O3 and use a mole-mole relationship to get to carbon monoxide. Now I'm going to look at the equation to fill in numbers that make that true. Be careful because I have carbon monoxide and carbon dioxide, so it's easy to get those visually just mixed up. So we need 3 carbon monoxide for every 1 iron 3 oxide. And now we have moles of carbon monoxide, but we're looking for grams. So I'm going to cancel out moles of carbon monoxide, and I'm going to go to grams of carbon monoxide. And now you have to go find the numbers that make that relationship true. 1 mole of CO. Can cancel my units, and now I have only the unit that I'm looking for. So that's how I know I'm done. So I can just multiply and divide these all together. So you can see we went from mass to moles, just looking at the numerator, then moles of iron 3 oxide to moles of CO, and then from moles of CO to grams of CO. We're going to do that same thing a couple more times. When in doubt, go to moles. And again, we started with 3 significant figures. So at the end, I'm going to round to 3 significant figures. How's it going? All right, so mass to mass calculations. You always have to go through the moles, and then this one would round up to 88.7. So notice I still have my number, unit, and label on that value. Do you see how the units cancel out? And in this way, we can use dimensional analysis to just step us through the calculation. Now I'm going to go forward into the next section where we're going to use these again and again, so you'll get really good at it. So when we have a chemical equation, it's kind of like a recipe where you go to your shelf and you look at what is in there. Maybe you want to make cookies and you need some flour and you need some sugar and you want some maybe chocolate chips or some nuts. So you have the ingredients on the shelf, and then you're going to take what you need for the recipe. But you won't have all the same amounts of everything. So maybe you'll run out of something first. That would be the limiting ingredient or the limiting reactant. So when we have a chemical equation, it's very rare that we have just the perfect amounts all together. Usually there will be one reactant that is limiting. If you have one thing that limits the calculation, then everything else will usually be in excess. So maybe you only have 1 cup of sugar. That means you're not going to make as many cookies enough cookies to use up all the flour, right? If the sugar is limiting, that's going to determine how many cookies you make. The reactants that are available in larger amounts don't get used up, so those will be in excess. So there's some extra. The reactant that gets completely used up is called the limiting reactant. So we can see it easily when we think about a bicycle. Maybe in the bike shop, you're not going to sell a bike with one tire. They don't sell that, right? They'll wait and they'll get a new tire and they'll sell a complete bike. So here's our recipe for the bike. We need a frame, we need a seat, we need 2 pedals, and we need 2 wheels. If the shop has 5 frames, from that 5 frames, we could make how many bikes? We could maybe make 5 bikes. If there are 6 seats, you could make 6 bikes, but there's only 5 frames, so you're not going to sell a bicycle with no frame, right? All right, now for 15 pedals, if you had 15 pedals, I'm going to write this out like a calculation because this is how we're going to do these problems. How many bikes can I make if I start with 15 pedals? Well, one bike needs to have 2 pedals, right? They're not going to sell a bike with 1 pedal. So here we get 7.5 bikes, but you're not going to sell a half a bike either. So that means 7 bikes. However, there's only 5 frames, so we already know we're not going to be able to make more than 5. What about 8 wheels? How many bikes can we make from 8 wheels? Well, there's 2 wheels for 1 bike, so that means we could get 4 bikes that are complete. So, if I ask the question, how many bicycles can we sell? How do we choose? Yeah, 4. We're going to pick the smallest value. So this is the one. This is the theoretical yield. We can sell 4 bikes. That means what was limiting? Wheels are limiting. Now, what if I asked you how many extra seats are there? So I'm going to say excess reactants. How many seats are left? That is going to be the number of seats we started with. We started with 6 seats. And then how many did we use? So initially, we're going to subtract 4 seats used. And then we have 2 seats left over. So we have to calculate how many seats got used. With bicycles and these numbers, it's pretty easy. But when we start looking at chemicals, that's a whole nother mass-to-mass calculation. The other thing that's really important to notice is that subtraction, right? We start with what we had originally and we subtract what got used. So let's do a couple problems like this with some chemicals. So here's our process. We need to calculate the mass or moles produced from each reactant given. So that's at least 2 parallel calculations. Then we're going to pick the one that is the smaller amount. The reactant that produced the smaller amount, that one is the limiting reactant. Remember, the limiting reactant is always a reactant. You'll never give a product as the limiting reactant. then whatever else is there is in excess. So I'm going to set up two parallel calculations. We're going to look for hydrogen gas. So how many moles of H2 gas could I get if I started with aluminum? Now the other one is going to start with my other reactant. How many moles of hydrogen gas can I get if I start with 5 moles of HCl? Okay, so now I've written down the question. Go ahead and follow that process. Right, I need to cancel out one unit and go to the other, changing the label. Then I'm going to fill in the numbers that make that true. We'll do that for both calculations. Now notice here I have to divide by moles of HCl in order to cancel that out, but I'm going to go to the same product. How many moles of H2 can I produce from that HCl? So I'll look up those values in the equation. And that's how many I can produce if the limiting reactant is HCl. Okay, so how much is actually produced?
2.5.
That's right, we take the smaller amount. So our limiting reactant is?
HCl.
Yeah, what we started with, HCl. And the reactant in excess will be the other one. It has to be a reactant. So don't give me a product. Make sure it's a reactant. That's going to be the aluminum. The expected amount is called the theoretical yield. That's how much we expect. So in this case, we expect 2.50 moles. So let's do another one. Again, we need to do two parallel calculations. And then this has propane. This is our propane right here. I like to label it to make sure that we don't get confused about which thing is which. And we're looking for CO2. Right, so we have two values, then we're going to pick the smaller one. That means we're going to produce that much from this reaction. So the limiting reactant is the oxygen. Make sure that you give a reactant. And the excess reactant is that propane. Now we can continue to work these problems. This was with moles, but remember we could put the molar mass on one end if we started with mass, and the molar mass on the other end if we need to end in mass. So let's do a couple moles. Yeah, this one goes to using the masses. So I'm going to write some information with the equation here, just so that I can see it and keep track easily. Now I'm starting with 50 grams of aluminum and 50 grams of HCl. So we don't know from the starting materials which one is limiting. And we are going to look for hydrogen. So again, we're going to have two parallel calculations. Okay, do you know what to do? All right, so I encourage you to be systematic. Think about what you're putting in the numerator of that mole-mole relationship, because one of the most common mistakes is that students will just put something else there and they calculate an amount, but it's not the one they're looking for. So make sure you pay attention to what you're looking for. That's why it's so good to write those question mark statements. All right. Oh, I see my mistake. Did you guys catch my mistake?
3 moles H2.
Yeah, right there. The limiting reactant is the same though, right? All right, 1.38 grams of H2. That's how much we expect. That is the theoretical yield. If everything goes according to plan, that is how much we would get. And that comes from the limiting reactant here, HCl, which means aluminum is excess. Now, in this case, we have a gas evolution reaction. You see it's a single replacement and that hydrogen's going to bubble out. So that's probably going to go pretty far to the right. But if we had an equilibrium, if we had a reaction that only goes like 80% to products, then we might have a less actual yield. Our actual yield might be lower than the theoretical yield. So this is our theoretical yield. And that's what we expect if everything goes as written. And we'll do another example before we start looking at percent yield tomorrow.